Thank you so much, Sasha. I really appreciate this opportunity to share with you what I consider the most substantial revision of magnetic stellar evolution in a generation. And I say that because it differs from the standard picture during the entire second half of main sequence lifetimes, which you'll soon see. So what I'll do is I'll review the key developments that led to this new picture, outline our current best understanding of the physical mechanisms that drive the transition, and finish with the latest results that combined ground-based spectropolarimetry to measure the large-scale magnetic field with space-based astroseismology from TESS. Okay, so we have seen this picture already, but just to summarize, the first half of main sequence lifetimes, magnetic evolution is dominated by rotational evolution. So stars are born with a range of initial rotation rates, and they spend several million years with their rotation locked to the protostellar disks before contracting onto the main sequence and spinning up slightly. And then magnetic braking kicks in, where they gradually lose angular momentum to their magnetized stellar winds. And this process depends strongly on the angular rotation rate. And so stars that are initially rotating more quickly spin down more quickly. And by 500 million years, stars of a given mass have converged to a common rotation rate. And that continues to the age of the sun, according to this diagram. And we had basically, as of 2008, we had no data between about 1 billion years and the sun's age. And we certainly had no data, reliable ages in particular, beyond the age of the sun. And so the punchline of this presentation is that somewhere around the middle of stars' main sequence lifetimes, rotation and magnetic activity actually decouple. So I'll show you the evidence for that. So when astroseismic ages first started to become available for field stars that were older than the sun from Kepler, Ruth Angus and collaborators were the first to notice something unexpected. They were trying to do fits of empirical gyrochronology relations to both young clusters and old field stars anchored using the sun, which is the red point in this diagram. And what they found was that the Kepler field stars didn't seem to obey the same spin down relations that you would assume if you anchor to young clusters and the sun. Their conclusion in the paper was that no single relation between rotation period, color, and age can adequately describe all the subsets of the data. In other words, they found different relations for different subgroups of the data. Now, the following year, Jennifer Van Saters and collaborators published a paper in Nature that went a step further. And they basically identified that there was a mass dependence to this behavior, such that hotter stars deviate from the standard spin down relation earlier at faster rotation periods and younger ages than cooler stars. And that dependence on spectral type suggested a connection to the Rossby number, because so the Rossby number is the rotation period normalized by the convective overturn time. And because stars with different spectral types have different depths of their surface convection zones and thus different timescales for convective overturn. But using that single parameter, the idea that there was a single Rossby number that all of the stars started to deviate from standard spin down, Jennifer and collaborators were able to reproduce the behavior in these old field stars using models that basically detailed rotational evolution models now, not just empirical fits, detailed rotational evolution models that turned off magnetic braking around the middle of main sequence lifetimes at a Rossby number comparable to the sun. Okay. Now, in a follow-up work, we found that this sudden change in rotational behavior also coincided with a change in the properties of stellar activity cycles. So this is a diagram showing the activity cycle period versus the rotation period. So keep in mind, this is in years on the vertical axis. It takes a very long time to get these sort of data. And this is a reproduction of a plot that originally appeared in Bohm-Vitan's 2007 with these two different sequences of activity cycles and the sun in the middle. And this was a long-standing puzzle. Well, by looking at a series of solar analogs, 18 SCO at 4 gigayears, alpha Cen at 5.5, and 16 SIG at 7 gigayears, this evolutionary sequence suggested that, in fact, once stars hit this critical Rossby number, the cycle period gradually grows longer before disappearing entirely or becoming undetectable. And this same pattern appears for hotter stars here. We're going to look more closely at this pair of hotter stars at the end, and cooler stars as well. And now we have a mechanism for understanding why the sun is between these two stellar sequences that Erika Bohm-Vitan identified. Perhaps the sun is on its way up, evolving slowly on stellar evolution timescales toward longer cycles with lower amplitudes before eventually the cycle will just disappear. Now, the following year, Cecilia Garofo and collaborators put forward this unifying explanation to describe both the existence of persistent fast rotators in young star clusters and these anomalously fast rotating old Kepler field stars. And that was based on the idea of how magnetic complexity evolves as a function of Rossby number. Okay, so this vertical axis is a magnetic complexity parameter. You can think of it as the mean spherical harmonic degree of the magnetic field. And so basically the idea was that in the saturated regime, you have very complex magnetic field that does not strongly couple rotation to the stellar wind. Eventually, once you get to the Scumanich regime, where stars spin down and their activity levels decrease in tandem with the square root of age, so these two parameters are strongly coupled, there you're at the bottom of this relation where you're dominated by a dipole field, for example, certainly low order fields. And then the idea is that late in a star's lifetime, it'll evolve again a more complex magnetic field that decouples rotation and activity once again. And here again are these stars that we'll discuss a little later. Okay. So what do the stars tell us about what is possibly going on to explain this kind of behavior? So I'm going to outline a four-step process of how we get from the Scumanich regime to this decoupled regime. So the first step is that slow rotation becomes non-differential. This is known from MHD modeling, where very fast rotators have sort of complex Taylor-Proudman kind of rotation states. But as a star approaches, as the rotation rate of a star approaches the convective overturn timescale in the convection zone, convection stops feeling the Coriolis forces that set up naturally this differential rotation pattern, and you tend toward a state of uniform rotation or possibly anti-differential rotation. So the main point is that as rotation, in the limit of rotation rate getting slower, you basically eliminate the ability to produce substantial differential rotation. Now, if you lose that differential rotation, it eliminates the shear that is responsible through the through the omega effect in stellar dynamos from converting a large scale field into smaller scale toroidal field that emerges as active regions. So you basically are severing the dynamo loop if you believe in something like an alpha omega dynamo in the sun and sun-like stars. So the loss of differential rotation severs the dynamo loop. That's important because the large scale field, the largest scale field that you produce from the dynamo is the field that most strongly couples the rotational evolution of the star through its magnetized stellar wind. Thank you. So the dipole field, for example, is responsible. So charged particles in the stellar wind are tied to the magnetic field lines until they approach the critical distance known as the Alfvén radius, where they then shed the angular momentum. And that Alfvén radius is by far much larger for the dipole component of the field and gets much smaller for progressively higher order components. So if you eliminate the dipole field because you've severed the dynamo loop, you lose your ability to efficiently shed angular momentum and change the rotation rate over time. And we know that stars gradually, their global dynamos shut down. Just empirically, that's true in the Mount Wilson survey. Young stars have high activity levels, high levels of variability, complex multi-periodic variability. But as they evolve, their average activity level comes down. They become less variable, more monoperiodic, until eventually you get these so-called flat activity stars where either there's no more large-scale variation, cyclic variation in the magnetic field, or we simply can no longer detect it because it's too small. Okay, so on to our recent results from LBT spectropolarimetry combined with astroseismology from TESS. Now, if you want to determine the morphology of the magnetic field in the large-scale morphology, spectropolarimetry is the tool of choice because it's most sensitive to dipole field, and then it progressively gets less and less sensitive because of geometric cancellation effects to higher order components. So you can think of spectropolarimetry as a spatial filter to detect or not detect large-scale field, and then you can use calcium H and K emission or some other magnetic proxy that's insensitive to polarity to define the relative activity levels overall. And so when we looked at this hot pair of stars where the active star 88 Leo is, shows normal cycles on both branches of the activity rotation relation, we actually detect a clear signature of a large-scale magnetic field dominated by a dipole with a strength of about 2.5 Gauss. For the inactive star, that's a flat activity star at a very similar rotation rate, we know its relative activity level from chromospheric emission, so it should be about 3/4 as strong as 88 Leo. So if you just scale down that detection in 88 Leo by 3/4, you would expect to see a 1.9 Gauss dipole field in rho Corbohr if you didn't change the geometry. But in fact, we set an upper limit on the dipole field in this star of 0.5 Gauss. And so the large-scale magnetic field is dominated in rho Corbohr by the quadrupole and higher order fields, just as we predicted. And very recently, we were able to get an astroseismic age for rho Corbohr and put it on this diagram. So the background gray points are the activity age relation from Lorenzo Oliveira for a sample of solar analogs. And the blue points are TESS astroseismic targets that we've put on there. With the exception of 88 Leo, this is the gyro age of that star. Now, so the astroseismic age of rho Corbohr places it out here at nearly 10 gigayears. If you determine the age of rho Corbohr from its rotation period, so the gyrochronology age is way down here. Now, both of them are below the sequence for solar analogs, and that's expected. They're more massive stars, thinner convection zones. And so, of course, at a given age, more massive stars are more evolved, and so you'd expect them to be less active. So this is just the mass dependence of the activity age relation. And we're working now to try to define in detail this activity age relation for all of the TESS astroseismic targets that we can get our hands on. Okay, so with that, I will put up my summary of conclusions and take your questions.
Thank you, Travis, for an excellent talk. I have some questions. So first question by Lauren. Even if the cyclic dynamo shut down, is there also evidence that the total amplitude of field becomes decoupled from the rotation? Or could there still be a steady field with the ability to affect the spin down?
I'm sorry, can you just repeat that? I didn't catch.
I say, even if the cyclic dynamo shuts down, is there also evidence that the total amplitude of field becomes decoupled from the rotation? Or could there still be a steady field with the ability to affect the spin down?
There is certainly still a steady field. You can measure the calcium H and K emission in these stars, and we think what happened, but it has no influence on almost no influence on the spin down anymore. And the reason is we think that this transition represents the loss of large scale field is what decouples the evolution of activity and rotation. You still have activity on small scales, say a local surface dynamo. So it's building field through an alpha effect driven by mechanical energy from convection. And that will continue to evolve with time, as we saw with the solar analog sample. The activity age relation is continuous, unlike the activity rotation, or sorry, the rotation age relation. So yes, it's the disappearance of the large scale field that is the event that effectively decouples the evolution of rotation and activity, but there's still activity to be measured on small scales.
So we are short of time. So just one last question, and then you can answer the questions in the Slack and chat, Travis. A question from Günther. For too slow rotation, any large-scale dynamo should die together with a differential rotation. You already see this limit.
What was that last part? I didn't catch the last bit.
You already see this limit.
The limit where the global dynamo shuts down? We think we do.
Where the large-scale dynamo shut down.
Yeah, the large-scale dynamo shut. That's what we think we're seeing. Admittedly, there are few observational constraints right now because we've only done these measurements for one set of stars like this, but there are more. We actually have LBT time this semester to do a sample of 5 additional G-type stars. And so we're hoping that there will be additional evidence very soon.